Welcome to our agenda, Bypassing Anti-Debug, a hybrid real simulate approach to Rootkit analyze, created by me and Hilberger. In the beginning of this agenda, I'm going to introduce ourselves. First, Hilberger. He helps a lot of these projects debugging and fix a lot of bugs. He is currently working at National Institute of Cybersecurity in Taiwan, doing malware analysis. But because he has some healthy issue, so sadly he cannot come here to stand with me. Next, me, Xuan. I'm a junior at National Sun Yat-sen University, majoring in computer science. Currently, I'm also an intern at Team T5 and working with the ATL team. Additionally, I am a competitor for next year's World Scale competition in the cybersecurity category. And the last, Artemis. She is also majoring in computer science at National Sun Yat-sen University, and she will help us to introduce the background and motivation of our design. This agenda will be hosted by me, Xuan, and Artemis. Let's get started.
In the first part of our agenda, I will talk about some fundamental background knowledge, including what is the rootkit and different methods for analyzing a rootkit in Windows. In the second part, I will discuss why one needs an emulator for analyzing rootkits, then talk about the existing emulator and talk about their pros and cons. The design of this emulator has combined some of other emulators' pros and eliminate some of other emulators' cons. In the third part, Xuan will talk about the design of their version of emulator, looking into the details of the techniques they use in their creation. After that is our fourth part, demo part. Xuan will use the emulator on a famous anti-cheat engine, which has a very high market share. About the name of this anti-cheat engine, well, if you know, you know. Xuan will break down the anti-debug and anti-analytic techniques that is used in their version of emulator. For anybody who wants to protect their driver from being analyzed, or even reinforce your products, you're welcome to refer to this part. In the fifth part, Xuan will talk about the overall evaluation and conclusion of their emulator. Last but not least, some upcoming refinements working in progress will be brought up at the end of the agenda. To set the stage, I'd like to start with some fundamental background knowledge. Modern operating systems are primarily divided into kernel mode and user mode. Kernel mode is running at elevated privileges compared to user mode. And the rootkit, which has an important role in this project, is a type of malware that resides in kernel mode. For anyone who would like to protect their systems, analyzing a rootkit is crucial. However, analyzing a rootkit can be challenging. Techniques such as virtualization or obfuscation make static analysis challenging. And most rootkits incorporate anti-debugging mechanisms, which makes them harder to analyze. Let's talk about existing dynamic analysis methods. Existing dynamic analysis methods primarily use dual machine debugging, where WinDebugger will be connected from one machine to another via network or COM interfaces. For example, we can use real machine, VMware, and KVM for dual debugging. There are also other hypervisor-based dynamic analysis techniques. Cheat Engine's function, dbvm, can do dynamic analysis of rootkit. HyperDebugger can do dynamic analysis of rootkit too. Or even, one can create his or her own hypervisor. And these three techniques are all based on EPT hook in Intel CPU. So far, we have talked about the fundamental background knowledge. Let's start diving into the motivation of this project and some related existing projects. For that, this project is creating a new emulator. Let's talk about the importance of an emulator. With dual machine debugging, it is possible to be detected to be in debug mode. Moreover, if one uses some virtual machine, such as VMware for dual machine debugging, VMware might leave some specific symbols that can be detected. Other hypervisor-based techniques will also leave detectable symbols, as shown on this page. One of the symbols is model-specific registers, also called MSRs. We will discuss how to detect hypervisor emulator by MSRs in the demo part later. We can see that there are several disadvantages in the mentioned analyzing method. However, for emulator, it has higher control and can prevent these disadvantages. This is why we need an emulator for analyzing rootkit. I'd like to discuss some existing emulation solutions by listing their advantages and disadvantages. There are 3 emulators that I'm going to introduce, which is SpeakEasy, Quilling, and Kernel Anti-Cheat Debugger. First, let's introduce SpeakEasy. SpeakEasy is an emulation solution that can load and execute PE files. By simulating Windows API, SpeakEasy can intercept parameters and send back the value it wants. SpeakEasy is implemented in Python, just like most of the emulators. However, there are some disadvantages of SpeakEasy. Firstly, SpeakEasy does not properly handle kernel mode structure exception handling. Also, there are some specific register operations that SpeakEasy cannot intercept. Second emulator is Quilling. Quilling is a well-known project and has the mentioned advantages of SpeakEasy. Quilling has an advantage that it is highly versatile, but there are still some disadvantages of Quilling. Technically, Quilling can support Windows kernel drivers. However, by looking into its source code, one can find that many functions does not do anything. They just simply return a value. Another disadvantage of Quilling is about structured exception handling. A recent added PR made Quilling support structured exception handling. However, testing shows that Quilling structured exception handling does not support drivers. So for a driver user, Quilling still cannot achieve structured exception handling. To look between SpeakEasy and Quilling, we can find out that, firstly, both of them are based on Unicode. Secondly, both of them rely on simulated environmental parameters, which are often fabricated. Thirdly, both of them fail to support structured exception handling-based drivers. Lastly, both of them lack the capability of multithreading. Here, there are 2 keywords: structured exception handling and multithreading. Before discussing about the last PE emulators, I need to explain why structured exception handling and multithreading are important. Structured exception handling, also known as SEH, is Windows exception handler. Without proper emulation, crashes or unintended paths will be triggered while facing errors. For comparison, in a desirable execution, these situations should enter the SEH caught exception, as shown on the page. While SpeakEasy facing an error, it will enter SEH, but the function of its SEH will leave the driver to be unloaded. While Quilling facing an error and enter SEH, its function will lead the system to crash. Without proper SEH support, an emulation cannot be properly executed. So now we can know that SEH is important for execution. Let's talk about another keyword, multithreading. To discuss about the importance of multithreading, please imagine the following situation. There are two threads, thread A and thread B. They are both accessing the same data. Thread B is about to write a new value to the data. Thread A is about to read this new value. So we can observe that thread B must execute before thread A in order that thread A get the correct renewed value. Without proper support, this situation may lead to incorrect execution flow. While SpeakEasy handling multithreading, all the threads are queued and executed in order, as you can see in this figure. So it is possible for thread A to execute before thread B. This will cause thread A to get the incorrect value. For Quilling's multithread handling, Quilling simply returns a fake handle without actually running the thread. The improper handle of SVH and multithread could lead to failure while emulating. That's why it is important for an emulator to handle SEH and multithread properly. Finally, let me introduce the last emulator, kernel anti-cheat emulator. Kernel anti-cheat emulator, also known as KACE, is one of the project's references. KACE maps drivers to user mode for execution. For that reason, KACE has native execution, and that speeds up the execution. KACE uses vector exception handling, also called VEH, for exception handling. For example, the attempt to read or write special registers such as CR3 will be handled via VEH. KACE has some advantages. One of its notable features is that it will use NTDO to get real environmental parameters. However, KACE still has some shortage. For that KACE is running in user mode, it has the possibility to be detected. For example, it can be detected by reading the RIP because the RIP's value is in user space. After seeing advantages and disadvantages of different kinds of rootkit analyzing methods and emulators, Shadowfeathers and HeroBurger wonder if they can create an emulator that combines the mentioned advantages and also fix the disadvantages at the same time. After researching and developing, they propose a hybrid, semi-emulated, semi-native approach using Unicore, enabling access to real parameter within an emulated environment. For that, all the operations is emulated in Unicore. All register can be mapped into kernel mode. Also, the emulator can hold the highest control over the process. As global hook being used, the emulator uses Unicorn's C++ bindings instead of the common choice Python.
Let's dive deep into the core of our project, the design and implementation of KDENU. In this session, we will walk through our main design choices, the problems we solved, and the key features that make our emulator a powerful tool for kernel driver analysis. So, what makes our emulator special? We built on the best parts of other tools, but added some key features of our own. The biggest one are using kernel dumps to create a very realistic environment, and strong supports for SEH and multithreading. These features are crucial for running the complex driver you see today. Here's how it works. First, we map out the basic system info to build an initial environment. Then, we load the driver that we want to analyze. As it's run, we watch for special instructions or memory access and log everything. When it's called a system function, we'll check if our kernel dump can deal with it or not. If it does, we run it directly. If not, we use hook to handle it. This mix and match approach gives us the best results. First, we have to initialize the emulation environment. To achieve this, we use a kernel dump to map the necessary system parameters. This dump is a pre-snapshot taken at a breakpoint set at the driver entry of any driver. Next, we overwrite the original driver with the target driver that we intend to analyze. To overwrite the target driver, we use the library, which called LIEF, to press the PE file. And while we use it, we discover out a security cookies bug in LIEF while making the emulator. So we report this problem and the PR is merged. About hooking, we start with an idea from Unicorn PE, which is to put a read instruction at the start of a function. But it can be detected because it's visible. So we made it better. Our emulator handles hook at function entry, then emulates the read instruction after emulating the function. And we also made one-shot hook to record the value that may be important. When we enter a function, it will trigger our first hook. It will set the second one-time hook as the address on RSP. Then continue execution the function. And when it's returned, it will trigger our second hook and we can get the value just from the function return. We also monitored data assist, a key feature inspired by SPEC. This lets us watch important kernel objects and log every time they are read or write in. But monitoring special instruction is stricter. Since Unicorn hook instruction is limited to just a few instructions like syscall and CPU ID. So for everything else, we built global hook. When our emulator is about to execute a special instruction, our hook steps in. It handles the logic, records the action, and then manually advances the RIP to continue execution. This approach gives us a complete picture of what the driver is doing. And we have two ways for the emulator to interact with the real machine. The first way, follow in KCE. We process anti-DLL function calls to update real machine environment's value. The second way, which is pioneering, is using kernel dumps. We got this idea from a fuzzing project which called What the Fuzz. And by using kernel dump, we can let the function have real parameters from pre-snapshot during function execution, yielding more realistic return. In summary, when facing a system function call, the emulator will check whether the function call can be handled via kernel dump or the function returns value will have anything may be detectable. If not, the emulator will proceed to hooking. About SEH. Before using kernel dump, our implement was complex. We emulate the full Windows SEH process in Unicorn, which we should have described in about 5 pages. However, after using kernel dump, we were able to implement it in another way. Remember what I said at the PE loading part? Overwrite kernel dump. There is a very important parameter that we need to overwrite from the kernel dump. It is inverted function table list. We will need to overwrite the pointer of original driver's exception table to the new driver's exceptions table address. This is crucial because if we didn't modify this, the system will not find the correct address to forward to when exception is triggered. After that, we can simply emulate to call RTL read state to handle the SEH. Another part, multi-threading. Because of Unicorn doesn't support multi-thread, so it is a pretty hard work. If we just create another thread and let different thread has the same Unicorn object, it will cause errors. So we tried two ways to deal with this. We first considered to use a single thread to run it. Content switching after a fixed instruction count on a shared instance. But this severely impacts performance. Ultimately, we adopted a parallel approach with static memory locking. During create thread, we hook all memory and restore content. Memory allocation is performed by main Unicorn instance and recorded. When a child thread accesses unmapped memory, it will check if the main instance has allocated or if it exists in the kernel dump. If so, it maps the data from the main instance or from kernel dump. Otherwise, an error will be triggered. Okay, enough talk. Let's see a demo. First, SEH. Look at the log on the screen. You can see the expression is called and the driver continues. It works perfectly. Next, multi-threading. See the two thread IDs. Thread A waits for thread B. Thread B does its work and signal. Then, thread A continues, reading the shared data. This shows our thread synchronization is solid. We are not sure detection techniques uncovered by emulating a real anti-cheat driver. You may ask, why not just use IDA? Well, static analysis is most impossible for this sample. It is heavily obfuscation using things like SEH for control flow. And it's packed with a VN. Trying to reverse that statically will be a nightmare. The following two pages list the monitored detection method that we discovered. We are not explore in depth into some of these techniques. First, we are going to talk about anti-debugging. They use int20 this instruction to detect PageGuard states. Int20 will trigger KISW interrupt to verify if PageGuard is enabled. The comment of EFI guards source code also explain about this skill. They also create callback to invoke PageGuard by another way. After search the hex that is set the callback, we can know that it's PageGuard TV callback, and it can trigger PageGuard as described on the block shown on slide. Next, dbg prompt. This function is for WinDebugger to print some debug message. When WinDebugger attached it, it outputs string to the WinDebugger's console. Otherwise, it triggers SEH. As shown on the slide, if we purpose to trigger an error with dbg prompt and handling via SEH, we can find whether it has WinDebugger or not. And this can avoid debugging in WinDebugger, quitting, or SpeedEasy. We will now talk about NSR-based detections, drawing from Secret Club's article. During emulation, anti-cheat read a non-exist NSR, triggering SEH for handling. Similar to dbg prompts, can detect whether it's in emulation environments or not. By using this, can also identify some known hypervisor. After we search this NSR value, we found the value is used by KVN. And so we think that maybe it's a detection of KVN. The anti-cheat also easily multiple exists NSR, such as writing 3 to dbg ctl NSR and resetting it to be 0. That's while flashing last branch records and branch trace flag to disrupt hypervisor-based analyze. And it also writes to L star NSR, which is pointing to KI system code 64 in default. PageGuard's editor blog notes this NSR is trapped by many hypervisor. PageGuard detects hook by writing a REST instruction and calling the system. By using our emulator, we can do deep analysis of this skill on the anti-cheat that we analyze. We found that anti-cheat writes a REST instruction on L star NSR and sets it to a previously self-allocated address. This process means it did the detection and hooking syscall by itself. It's also used last branch NSR. Some hypervisor fail to restore state information during VN access. So, by reading the NSR and doing force VN access, then read NSR again when the function when the system enters the VN. The system can check if the value of last branch NSR is different from the past. If the value do differ from the past, that means the environment is virtual. Also, we discovered that it uses NI capture image exception value to find OS-dependent offsets. Uncloned cheats form mention this function for getting offsets. We can also find that Backbone's source code use it to get the offset. So, we can see that this anti-cheat engine implements many advanced techniques. Although this anti-cheat engine has many advanced techniques, we still collected some of the easier methods that can be implemented. For the listener who would like to prevent driver analyze, you may start with this method shown on slide. Also, it should be noticed that some of these methods had to be constantly repeated, such as reading the cache user share data and DR7 writes. Finally, we evaluate our project. Compared it to other emulators, we provide native SEH support and parallelized multi-threading. Compared it to KACE, we ensure full kernel space execution. By doing so, we combine their good parts while addressing weakness. The future plan. We hope this project can be an alternative for driver or Rootkit analyze when hypervisors methods like hyper-debugger or cheat engine DBVN fail. After post submission in July, we implement kernel dump functionality. By doing so, we let the emulator's environment more realistic. Just like what we just said in the SEH part. Almost function can be handled via kernel dump, except file system or another need to interact with hardware. Finally, the project will be open sources, and now it's open source. In the last, I would like to thank the mentors who gave me advice on this presentation. First and foremost, I want to thank my team at Team T5 for all their help with this presentation. I'm especially grateful to my supervisor, Kenny, and Zeze, a former Kobu speaker, and Liam from D39 team for their feedback and suggestion. I would also like to thank other seniors in Taiwanese cybersecurity community for their guidance. particularly ADR from Kita1 and the other speaker also in this session, Angel Boy. And here's all my presentation, and the source code is on the QR code. You can send it. And right now it's already have about 100 and about 40 starts. And right now can ask the question.
So I'm wondering, you said for calls to NTDLL, right now you proxy them and forward them along to kind of the system NTDLL. Are you worried about how that might affect, like, someone could add some new detection technique based on something like that? Or have you thought about kind of what that might look like in the future?
That should not defect to the feature that we add to. Just our implementation is like, if a function cannot execute in default, we will just hook it. And if it can execute in a normal way, we just delete the hook and it's okay. Yeah.